Let's take a look at the first and second derivative tests. We're going to do an example of each and then compare the things that are similar and different. Before we look at those examples, let's take a graphical look at this. First derivative first. Pretend this is a tangent. This guy is a horizontal tangent line. That's when the first derivative is equal to 0. We do lots of that where we're setting the first derivative equal to 0 and we're looking for these peaks and valleys within a graph. But what we also get is that when a tangent line is positive slope, then it looks like this. And all of them over on that left-hand side have that. And over here, these tangent lines are negative slope. And so the tangents actually move around with the curve. So they are positive, they're getting to be smaller and smaller and smaller, positive numbers still, but smaller and smaller, approaching 0 until they become 0 slope. And that first derivative becomes 0, and then the first derivative is negative. Negative slopes all through here, and then we get to a transition point here, and then they're becoming larger negative. Then they become smaller negative again, meaning smaller, in size, so closer to 0, which is really larger. Wrap your head around that. And so they go down here until they reach 0, and then positive again, small positive, bigger positive until this transition point, and then smaller and smaller positive until they approach this 0, and then negative and more negative as they come here. So that's the first derivative. The second derivative is looking at concavity. And so it is looking at this idea that over here we have concave down, concave up, and then concave down. And where they transition from concavity up to down or down to up, we get these points of inflections, and that's approximations where those are. And so second derivatives are really looking at concavity, the changes at which give you points of inflection. And the test itself is telling us that if we take this first derivative and the critical value of the first derivative where it is 0 here, and then we put it in the second derivative, it will tell us whether it is concave up or down. And so here we would get a negative number showing concave down, so this is a max. Concavity is up here, and so here we have a min. Concavity is down here, again a negative second derivative, and so here you have a max. Let's do an example. Go ahead and write this function down. We're going to real quickly review what the steps are for the first derivative test. And so when you're doing a first derivative test, you're going to find the first derivative, then you're going to find the first derivative critical values, and that's where it's 0 undefined, and then you're going to mark them on a number line, and then use pluses or minus where you indicate whether the derivative is positive or negative. You should build a frame if you're being asked for a function and whether it's increasing or decreasing, and you're going to use the first derivative test. This is the frame that you use. You need the first derivative, the critical values of the first derivative, a sign chart of the first derivative, and then you draw your conclusions. So if you're going to use the first derivative test, set up this frame first, then you go back and we get to work. And so for this one, the first derivative is 2x to the fourth becomes 8x cubed is the first derivative of that term. Minus 12x squared gives us minus 24x. Derivative of 5 is 0. We need the first derivative critical value, so 0 or undefined. This guy is never undefined, but he can be equal to 0, and so we set it equal to 0. Factor out an 8x. You get 8x squared minus 3 inside. So this is telling us x is 0, and on this one, set x squared minus 3 equal to 0, add 3, take the square root of both sides, so you get plus or minus root 3. These are the critical values of the first derivative. So first derivative critical values. Now we're going to put this on a number line, and so we have negative root 3. First derivative is 0 there. At 0, the first derivative is 0. At positive root 3, the first derivative is 0. And we now need to test values in each of these intervals in between. So here. So we've got 4 intervals. Pick down here, let's do negative 3. We're substituting into the first derivative, and when you do that, you get a negative number. Pick -1 in here, substitute it into the first derivative. You'll get a positive number. I'm not walking you through that substitution. Here we have pick 1. It's between 0 and √3. You can pick any number in that interval. Really, it doesn't matter. And substitute that into the first derivative, and you're going to get a negative number. And then out here, let's go ahead and use 3, and you get a positive. And so what this is saying is that you have negative slope tangent lines here, positive here, negative here, and positive here. That also is saying it is decreasing, then increasing, then decreasing, then increasing. And so we can go ahead and write those intervals as our final solution. So it is increasing on -√3 through 0. We're writing the x values on which this is occurring. Union, meaning and, we're gluing them together. And from √3 to infinity. And then decreasing, write the intervals on which it is a negative first derivative. So negative infinity all the way to -√3, union, and 0 all the way to positive √3. So this first derivative test has shown us that we take that first derivative, critical values, put them on here. We're really seeing where the slope of those tangent lines are negative, so it's decreasing there. Where it's positive, so it's increasing there, and we're done. We can also do a follow-up question using that same first derivative sign chart. So let me just real quickly recreate that here. And we tested each of these intervals in here, so I'm just going to put those, what we found inside here. What this is saying is it's asking you where the relative max and mins are. Since we know it's decreasing here and increasing here, there is a min at -√3. So a relative at -√3. And then increasing to decreasing. So here, there's a relative max at 0. So relative max when x is 0. And then, of course, it was decreasing and then increasing. So here we have another relative min at positive √3. Now, we do need to find the y values. That's what's sitting inside here. So this is f of -√3. And go find that value. You're going to find -13. Do the same thing for the other two x values. Substitute them into the original equation to find these y values. Again, I'm not going to walk you through that substitution. Just know that you're putting it in the original. And so that sign chart that we did the first derivative test on, that can, for us, find increasing and decreasing, but increasing, decreasing also gives us this relative max and min. Let's turn our thoughts now to the second derivative test. Here's our function, and we want to find all relative max and mins for this particular function's graph. Let's remind ourselves of what the second derivative test is asking us to do. We're going to find the first derivative, then we're going to find the first derivative critical values, and then the second derivative, evaluate the second derivative at each of the first derivative critical values, and then we can draw our conclusions based on the second derivative test. Let's walk through that. The first thing you're going to do is set up your frame. Again, here's our function. For the second derivative test, we need the first derivative, its critical values. The second derivative, evaluate that at each of these guys, and then draw our conclusion. And so whenever you do a second derivative test, set up the frame, and then get to work. So the frame first, then start working. And so take the first derivative. X cubed gives us 3x squared. Minus 3x squared gives us -6x. 6 gives us a derivative of 0. Critical values, we need to know where it's 0 undefined. This guy's never undefined, so set them equal to 0. Factor out a 3x while you're writing, x minus 2. So that gives us x equals 0 and x equals 2. Remember, these are the first derivative critical values. We then need the second derivative, and so derivative of 3x squared is 6x. Derivative, so we're taking this guy and taking his derivative, minus 6. We then evaluate that second derivative at each of the first derivative critical values. So this is where it is so ultra important to watch your notation, right? You've got to really make sure you are writing down what is what, because otherwise you're going to get them confused. So let's substitute 0 into 6x minus 6 gives us negative 6, which is less than 0, which means the concavity is down, which means we have a max there. And the second derivative evaluated at 2. 2 times 6 is 12 minus 6, which is greater than 0, which means concavity is up, which means here we have a relative min. So we have a relative min when x is 2 and a relative max when x is 0. Then we have to go find those y values. We're going to substitute back into the original function. And so when we do that, we get a 2 and a 6. So for the second derivative test, here's our function. First derivative CV. Second derivative, test the first derivative CV into the second derivative. Watch your notation. And then name your conclusion. And the conclusion is based on this logic statement of what the concavity is doing, what's occurring. And you're going to find actually sketching the little concavity curve is going to help you name max and min. Go find the y values. That's what these guys are. And remember, there's a third line on the second derivative that says, if the second derivative evaluated at a first derivative critical value is 0, it's no conclusion. But when we tested both of ours, we got a number, not 0. So there is no conclusion line on this particular example. Let's go ahead now and compare these first and second derivatives. This column is first derivative, notice sign chart. Here's second derivative, no sign chart. For both of them, you're going to find the first derivative and the first derivative critical value. So that's a similarity. But then what occurs next, here in the first derivative test, we mark it on a number line, mark the number line, and then we draw a conclusion. Whereas over here on the second derivative test, we have to find the second derivative and evaluate the first derivative critical values there, and then we draw our conclusion. And so we have this similarity of starting with the first derivative, and then the processes diverge at that point, where here we run a number line, and here we run a second derivative. Both of them we have a conclusion. Now what you see in the middle is this finding a point of inflection using concavity. And so you do a second derivative critical values. Interesting, right? Haven't done that yet. So this is really a second derivative number line where we're marking that number line with those critical values and then naming a point of inflection if we have a change in concavity. And so similarities for first and second derivative test differences, and then this oddball in the middle, which is finding points of inflection using concavity of the second derivative. And so that is it. Hope you are having a great day.